What is vapor pressure? My favorite example of a vapor pressure is when I mow the lawn. You got one of those red plastic gas cans and you set it out in the sun. What does it do? Yeah, it gets all tight. Gas has a low heat of evaporation. We say it's very volatile, and it builds up a pressure. At any temperature, some of the molecules in the liquid have enough energy to break free. The gas isn't at its boiling temperature. Water does the same thing. You just collected hydrogen gas over water and you accounted for the vapor pressure of water in that experiment. And as temperature rises, the fraction of molecules that have enough energy to break free increases. So here we see some ethanol. Somehow we might freeze this, evacuate this tube, let it come up to some temperature and see what pressure is developed. So the boiling point, what is a boiling point? Or what is the definition of boiling? It's when vapor pressure equals atmospheric. The boiling point of a liquid is the temperature at which its vapor pressure equals atmospheric pressure. So here we see the normal boiling point for various substances. Here's water, and what's magical about this 760 torr? Yeah, that's our normal atmospheric pressure. And you can see as pressure decreases, so does the temperature. So we're at mile high here, and we don't always get water boiling at 100 degrees Celsius. And then ethylene glycol has a bunch of OH groups, can do a lot of hydrogen bonding. Diethyl ether, weak intermolecular forces. Put that on your hand and your body temperature will boil it. Your body's temperature is like 37 degrees Celsius. So this thing gets kind of studied out, and if we take the log of vapor pressure and plot it 1 over the temperature, that's the Kelvin temperature, we find out that the natural log of the vapor pressure of a liquid is inversely proportional to its temperature. And of course, when I see something like this, I think, oh, if we could plot this, we can probably calculate a enthalpy of vaporization. And here we see how that just might work out. So we have the natural log of pressure, the inverse of temperature, and it's got to be in the Kelvin scale. And if we look at this, we might think y equals m, and t is our x, plus some y-intercept. So we might see the equation of a line.
So does that mean the opposite of delta heat? Because its pressure equals...
Just has a negative slope. And this is kind of nice because there's at least 3 things we can calculate. If we know all the other things, we can calculate a heat of vaporization if needed. We can calculate a vapor pressure at a new temperature if we know the heat of vaporization. And we can calculate a temperature if we change the pressures and we know the heat of vaporization. 3 things we can do with this equation. Use the following data to determine the molar heat of vaporization of chlorine gas. So what we want to remember is that I have natural log of pressure along one axis, and then if I plot 1 over t, I get a slope, and that slope is equal to negative the heat of vaporization over r. So if I can just get a couple points on here and solve for the slope, and once I have the slope, I'm going to need to multiply by r. So the first thing we might want to do is find the natural log of 40. Natural log of 40, plug that into your calculator, and you should get something that looks about like this. And then off to the side, we might need our formula for Kelvin. If we know degrees C, 273.15. And so my Kelvin temperature here is going to be something like 188.65. Now on my calculator, I have this little key that looks like e to the negative x. Excuse me, that's a Freudian slip of something that's coming up. x to the negative 1, that finds the reciprocal. So that means if I take 1 and divide 188.65, so here's my 1 over k, I get something that looks like 0.0053. Alright, so now I have a y value and I have my x value. So now I'm going to take the natural log of 100. So there's my natural log key. Put 100 in there, in the parentheses, hit enter, and I get 4.6 and some change. I'm going to write that down here. 605. And we could maybe do more digits, but I'm thinking that's going to be enough. All right, well, I need to take negative 71.2 and sum it together with 273.15. We can see we've gotten warmer. Still pretty cold. All right, so there, just want to show you on the calculator. There's my Kelvin temperature. There's that little key. I hit that, hit enter. All right, so then I found the reciprocal. I divided that Kelvin temperature into 1. I'm going to write that down right above here. And then I'm going to round it to there. So now I think I should have most of what I need here. Y equals mx plus b, our equation for a line. So another way to think about slope is rise over run. What is my rise? That's going to be my, well, we're plotting the log of pressure. So there's my rise. Oh, I see what everybody's trying to tell me. My bad. Excuse me. I always tell students, it's a good thing I'm not trying to chew gum up here. Things would really go downhill. All right. Yeah, so my run, that's the x value. So doesn't matter which order you do these as long as you keep them in the same order. So I'm going to have to put my, that's wrong, 0, 0. Do that on your calculator and it probably spits out some number like this. Now, what are the units on this number? This number up top, the log of pressure, and in that Clausius-Clapeyron equation, in the 2-point form, we have a log of ratio of pressures. So I'm going to say the units in that don't matter, but down here it's reciprocal temperature. So it turns out we actually have a K up there. Now what is this equal? Let me come down here and write it. We have a little better room. This equals negative the heat of evaporation over R. So now if I multiply both sides by R, and we're given R up here, I'm going to pull out my R. This is joules per Kelvin per mole. All right, now I'm going to multiply it by this number, negative 2632447 K. So I wanted to throw in some of those units there. So your K goes away, and I'm going to be left with a unit of joules per mole, which makes sense for a heat of evaporation. All right, then I pull out my calculator, multiply these two numbers together, but maybe before I do that, I have a negative and a negative. So I can multiply both sides by negative 1, or there's a negative here. At whatever rate, my calculator actually gave me a negative value here, but I'm going to say, well, so this is joules per mole. And we might say that equals the negative heat evaporation. So multiplying both sides by negative 1, I get a positive value. Now if I convert this to kilojoules, and then if I round to 3 digits, I'm going to get that number there. So a chemist can put a liquid in a flask hooked up to a pressure gauge made out of mercury, change the pressure and measure a couple different temperatures, and then calculate the heat of vaporization. And then that heat of vaporization with Hess's law seems to hold true. Other ways we might be able to do it, evaporate some of it and measure heat change. So all the numbers are good. Here's a typical problem to use the Clausius-Clapeyron equation. Now, before we're able to use this equation, temperatures are in Kelvin. Alright, so now we're ready to solve this problem. The molar enthalpy of vaporization of boron tribromide is 30.5 kilojoules per mole, and its normal boiling point is 91 degrees Celsius. what is the vapor pressure of boron tribromide at 20 degrees Celsius? So what we want to do is find a different vapor pressure. I'm going to just call that vapor pressure 1. And so pressure 2 becomes the normal pressure, standard pressure, 760 torr. And now I want to take my kilojoules there and turn that into joules, because R is in joules. And my 293 right there. Now everything on this side of the equation can be evaluated. Here's how I'd probably proceed with my calculator. There's what's in the parentheses. I'm going to go times 30,500 joules, divide 8.31. Alright, so now to use our property of logs, and so on my calculator I'm now going to go e to the x, put my answer in there, and out pops a number. Now to finally get to x times 760 torr, and we see that right here D is the correct answer. So given a heat of vaporization and 2 temperatures, solve for a new pressure. Now we're going to use our same equation here. At what temperature does ethanol boil on a day in the mountain when the barometric pressure is 547 millimeters of mercury? The heat of vaporization of ethanol is 39.3 kilojoules per mole, and its normal boiling point is 78.3. And once again, I want to turn this into joules. So where the decimal was, I'm going to make that a comma, multiplying this by 1,000. There's my 39.3 kilojoules, 39,300 joules. Now it's compatible with the units of R. So my new pressure is P2. So that means my T2 is going to be my X. So here's my temperature in Kelvin that ethanol boils at 760 torr. So I can do that side on my calculator. And then let's bring this to the other side. I can determine this number and bring it on across. And when I get done doing all that, if I did it correctly, I'm going to have something that looks like, so solving for X. Alright, so that is the Kelvin temperature. So now if I minus 273, and that's going to be this